This is the immensity of space. Absolutely incredible place that we live in, that lives up there. You know, it's thought that there's between 1 and 2 trillion galaxies out there. And this one, the Milky Way, our own galaxy, has maybe got something like 100 to 400 billion stars, of which one of those stars is this one, the Sun, around which we have these planets orbiting. And then as we move through an asteroid belt, a belt of huge collisions to get to the rocky planets. And here are the rocky planets. And of those rocky planets, of course, the third one from the Sun is a very special one, because that is Earth. That is our planet, that is home. And it is the most remarkable place, an extraordinary place. Look at it, protected by a magnetic field that's been blown by the solar wind, so you can see the solar wind pushed out beyond. But that magnetic field gives us protection from solar radiation. It's allowed life to start. The location of the planet in relation to the Sun has allowed water to exist in all 3 states, as solid, liquid, and as gas. And as a result, this is certainly the only place we know in that whole huge multiverse that has complex life. And that planet is the planet that's in peril. Welcome to Expedition Earth, an explorer's guide to a planet in peril. I'm Iain Stewart, and I'm an Earth scientist, so I'm interested in how the Earth works, its history, and what it means for us. And that means what happened in the past, what's happening in the present, and perhaps most importantly, what's going to happen in the future. And the thing is that Earth scientists look at the planet in a different way. So if we look at a map of the world, since the beginning of explorations and seafarers have been going around charting our shores, we've seen this pattern, this very familiar pattern of the globe that a school kid could pick out, of the different continents scattered around the Americas, Africa, Asia, Europe, Australasia, and Antarctica. But that world is just a snapshot. It's just one world that we have right now. If you go back through 4.5 billion years of Earth history, multiple worlds have changed and evolved. And that's what Earth scientists are interested in. And it's the expeditions that have uncovered those past worlds that are fascinating to me. Expeditions like Robert Falcon Scott's Terra Nova expeditions. So around the turn of the 20th century, Robert Falcon Scott decided he wanted to go to the South Pole and reach the South Pole, first person ever to do that. So he put together this Terra Nova, the new land expedition. Leaving from Plymouth, from his home, his great son of Plymouth, that was what was the plan. But one person was desperate to get onto that expedition, and it came from an unlikely source. This is Marie Stopes. She's much more famous these days as being the pioneer of women's rights, but actually back then she was a paleobotanist. She studied ancient leaves and seeds, particularly from the Carboniferous period, 300 million years ago. So plants like this is something called Glossopteris. You can see the little leaf-like shapes. Now this had been found in India, had been found in South America, South Africa, Australia, and she was certain that these would be found in Antarctica as well. Not the place you'd expect, that's frozen wilderness, but she was thinking the rocks would contain Glossopteris. So she pleaded with Robert Falcon Scott, take me on the expedition. But Falcon Scott realised that this was going to be one hell of an endurance journey, and said that what he would do instead is he would collect rocks for Marie Stopes. And that's what he did. He had a geologist as part of his team, and as they went on their expedition to reach the South Pole, he got his team collecting rocks, geologizing on the way. Now, of course, it ended in tragedy. He reached the South Pole, but too late. Amazon had got there, and they started the trek back. I imagine completely despondent, but still geologizing, going away, collecting rocks, man-hauling huge amounts of rocks, such that when they never, of course, reached back to their original stores. They ended up dying in a tent, just a few miles away. But even in that tent, when the bodies were found, all the rocks were laid out, including this one. This is one of Scott's rocks, and you can see here these telltale signs of ancient leaves of Glossoptera. Murray Stopes was right. Glossoptera was also found in Antarctica. So go back 250, 219 million years. If you were an alien spacecraft going across the Earth, this is what the Earth would look like. A single united landmass, Pangaea, all Earth, surrounded by ocean, Panthalassa, all ocean. And that, it turns out, is the way the Earth works. It's constantly creating these huge land masses, then scattering them to the four winds and then bringing them back. So you have these multiple supercontinent cycles. And so you start to get the realization that the Earth is not just this planetary body, it's a machine. It's a machine that's constantly kind of changing. So this is us catching the Pangaea starts to break up about 201 million years ago, starts to go separate ways. And here we have a snapshot capturing 100 or so million years into that journey, where we're starting to get the familiar geography of the continents, except in a few places. Australia still connected to Antarctica. How mad's that? The red continent of Australia connected with the white continent of Antarctica. Australia is going to move northwards. India, sitting beside Madagascar, about to go on a journey into the northern hemisphere to clash into Asia and produce the Himalayas. So we have this incredibly dynamic planet. And that's driven by heat. That's driven by the fact that the planet is losing heat. It loses heat from its hot inner core, which comes from the original accretion of the planet 4.5 billion years before, and also from radioactive heat given out by radioactive elements in the mantle and the crust. So all this heat is coming out, driving this incredibly dynamic process. Now, way back at the start of geology, James Hutton in 1788 came up with the theory of the Earth, which is the first big-scale integrated theory of how the planet worked. He didn't know what was happening, but he knew that heat must be important. He talked about an internal fire or power of heat, a force of irresistible expansion in the body of the Earth. So somehow heat, the loss of heat, was making Earth kind of active and dynamic. So today we have this as plate tectonics. The idea that the loss of heat turns into this convection movement that keeps the shell, the outer thin shell of the planet in constant motion, sometimes sliding past, sometimes pushing together, and sometimes separating out. The Earth is a colossal recycling machine. It recycles the Earth's crust, but alongside that it recycles most of the chemicals, most of the water that we've ever had. So we think that the planet has got the same amount of water now as it's probably ever had, ever since very early times. And that's been because of this constant recycling machine that we live in. And if we look at some of the effects of that, some of the outward effects of that process, this shows us just how dynamic the planet is. This is actually showing earthquakes that are recorded in yellow, and also you'll see some orange spots, that's the volcanoes. And you can see the pattern of the plates, the edges of these rigid blocks. And along the edges is where the geological actions, where seismic energy builds up of volcanic eruptions. You can see pink here. These are areas of deep earthquakes where one plate is getting pushed down and underneath another, what we call subduction. So you can see that process is the cracks, the outer cracks of the Earth as it releases this heat and this energy. And you can also see the cities, some of the cities on there. Many of these earthquake zones and volcanic zones are in places where we've got big cities. But is it just a machine? I mean, this was a question that Hutton had. Hold on a minute. He says, is it merely a machine, or may it not be considered an organised body, such as has a constitution in which the necessary decay of the machine is naturally repaired? A naturally repairing machine. Now that is very similar to a much more modern idea that James Lovelock came up with, which is Gaia, Mother Earth. The idea of a self-regulating organism, that the Earth's biochemical cycles are attuned to life, and they give the conditions that are good for life to be created and to be maintained. Now, when Gaia came out as an idea in the 70s from Lovelock, Geologists hated it, absolutely hated it. It was all that mythological rubbish. But actually since then, that idea of the interconnections, the coupling between the lithosphere, the solid earth, and then the hydrosphere, water, the atmosphere, the cryosphere, the ice, and of course the biosphere, that interlinkage is now part of modern geoscience, except we don't call it Gaia, we call it Earth System Science. Personally, I prefer Gaia. But the point is that we live in the most dynamic of environments. And those dynamic environments are critical because of life. So in this second part, I want to look at life and the importance of life. Now I got a real introduction to just how important life was in terms of for me, for example, a few years ago when they locked me inside this airtight vault down in the Eden Project in Cornwall. So the backstory here is I was filming for a series called How to Grow Your Planet. And we wanted to look at a famous experiment that happened in the early 1700s by Joseph Priestley. And Joseph Priestley had taken a mouse and put it in a bell jar, and eventually when the mouse used up the air that was in there, the mouse died. So he was interested in what air was. Eventually ended up putting the mouse into the bell jar with a sprig of mint. And the plant, the growth of that mint, allowed the mouse to survive. So he realized that the plant, the mint, was giving out some kind of resource that the mouse was able to take in. And that led him eventually to recognize and discover the importance of different gases in the atmosphere, particularly oxygen. So here the idea was, hold on a minute, I'm the mouse. What if you put a geologist inside an airtight box, take the oxygen down really low, stick in a whole bunch of plants and see whether the plants would keep me alive? Because in the box I'll still be breathing, I'll be drawing in oxygen, pumping out carbon dioxide. The plants would be taking in carbon dioxide and pumping out oxygen. Could we keep ourselves in balance? So we ran this experiment over 48 hours. Everything was monitored because this was, we were going to take the oxygen levels down to about 12%, which is pretty close to hypoxia, quite dangerous. If I took in any more oxygen or took away more of that oxygen, I was in danger. So here we have a doctor who's been monitoring this. And I always like looking at that because it looks like I haven't seen a woman in months, but actually that's like several hours in. I'm already really tired. You can see here the carbon dioxide level in the thing going up, down when I'm sleeping, back up again, and then it starts to tail off. But the really interesting one's the oxygen. Here's the oxygen level. So right at the start of the experiment, we go back down to almost at 12, and then you see the plants kicking in, gradually taking in that CO2, including my CO2, and pumping out oxygen. And I think what's really interesting here is that it gives you an idea of how much of that natural world you depend on. For my well-being over just the course of 24 hours, doing nothing in a box, I required all of that vegetation just to keep me alive. So you start to think about that, how that gets replicated across the planet for, you know, the 8 billion people that we have on the planet. In terms of carbon dioxide, it's the thing we're all talking about at the moment in terms of climate change, the role of carbon dioxide. We've known about the importance of carbon dioxide as a warming agent in the atmosphere for 150 years or so. But we've only really been measuring its effect since the late 1950s when Dave Keeling started to measure in Hawaii, in the Mauna Loa Observatory, started to measure carbon dioxide levels. So around the 50s and 60s, couldn't really measure anywhere in the cities. The cities had smog, and they were horrible pollutant places. You had to get away from civilization to get pristine measurements. So he went to the middle of the Pacific, and he started to measure these things. And he started measuring, and there was around about 311 parts per million. And he measured over, just after the first few years, you could see that there was a rising trend. There's a rise and fall each year. That's a seasonal change. And is dominated by the northern hemisphere vegetation and land and forest. So in the springtime, the new growth of plants and trees happens in the northern hemisphere. It drags in all this carbon dioxide, and so levels drop down. Then when the autumn and winter comes and all that vegetation dies off, CO2 gets released again to the atmosphere. So the southern hemisphere has an effect, but it's not as big. So you see this rise and fall, almost like the breathing of the planet. but gradually, imperceptibly, but undoubtedly increasing. And that was recognised even at the time. So we have this remarkable thing that I was born in 1964. A year after I was born, 1965, President Lyndon Johnson gives a message to Congress. And in it, he says, this generation has altered the composition of the atmosphere on a global scale through a steady increase in carbon dioxide from the burning of fossil fuels. So this notion that CO2 levels, the greenhouse effect, is intimately connected to a burning of fossil fuels is something that's been known about for 50, 60 years. It's not new. The science was very well established in that way. But you can see now, we're not at 311, 12, we're at 412, 100 parts per million more. And you think, well, actually, 100 parts per million? That's not very much, 100 parts per million. Surely, is that a problem? Well, you only realise that it's a problem when you see it in context of a longer history. This is truly remarkable. We have been able to establish a history of carbon dioxide record on our planet in great detail going back about 1 million years. And that's because we've collected ice cores from Antarctica and Greenland. And the Antarctica ones particularly go back a long time. We can see one here going back 800,000 years. And what it shows is we see all these fluctuations in carbon dioxide, going from about 180, 280, back and down, up and down through time, over hundreds of thousands of years. And that is relating to the orbital changes. So the relationship of our planet as it moves around the sun and tilts, etc., different amounts of radiation get passed on to the planet. And that warms the planet or cools the planet. So we go in, these are ice ages here, when we get a very low greenhouse effect of the carbon dioxide, to what we call interglacials here, which is when we have the higher greenhouse effect, the warming. So we see it bumping up and down between those two levels. Modern humans, we come in about here. So this is about 4 times longer than modern humans have been on the planet. So as you come out of the last ice age here, it comes up, you would expect, if you'd known that record, for it to get to about here and it would go back down again, because surely that's what it's always done. But it doesn't do that. It keeps on going. Breaks through 300, breaks through 320, 350, 380, 400, and we get to 412. So we have put 100 parts per million into the atmosphere in our watch in the last generation, or few generations. 100 parts per million is what it sends the planet in or out of ice ages. So you have this idea of the climate being finely tuned and us pumping it full of this substance, which is actually the thing that drives climate change. And the atmosphere doesn't care where it gets its carbon from. In this case, it's getting its carbon from us, from fossil fuels. But it's not just that long-term carbon dioxide change. This is referred to as the Great Acceleration. This is indicators from the human world, from the economic world, social world, and also from the natural world of changes that have happened since 1750 through to today. And what we see is relatively little change through the early part of the Industrial Revolution, into the 1900s and into the early 2000s, and into the early 20th century. But what we see is that as soon as it gets to the mid part of the 20th century, particularly the post-war economic boom where there's industrialization everywhere, everything just goes haywire. We start to use, the human machines start to really take off, and it requires a huge amount of resource that's affecting the oceans, affecting pollution, affecting the temperatures in the atmosphere. There's not a bit of our planet that's unaffected by this remarkable changes. In the 1950s and 60s, we're doing bomb testing. So we're actually putting artificial human-made substances into the natural environment. And indeed, it's those artificial radioactive substances that we did from the bomb testing, which is arguably the start, that starting point from the human age. This reminds us really that the climate system is really complex, finely tuned, but it has tipping points. It has parts that are very sensitive to change. So things like, for example, the West Antarctic ice sheet. So that's an area that if we lose that can really dramatically increase sea level changes, to some extent also the East Antarctic ice sheet. The Amazon rainforest, the so-called lungs of the earth, well, it's certainly a critical habitat, critical area of importance for the planet, and we're losing that strongly through deforestation. The coral reefs, across that we're losing the biodiversity, critical biodiversity that underpins the food chain there because of global the warming of the oceans and increasing ocean acidification. And then we go up to the boreal forests of northern Canada, or the Atlantic circulation. These are fundamental parts of our climate. The changes in the Greenland ice sheet, where we're losing more and more of the melting of the Greenland ice sheet. The loss of the permafrost tundra, where the frozen ground is now melting, releasing methane. It's a really potent greenhouse gas that puts carbon into the atmosphere. And then the Arctic sea ice, the extent of that's dramatically been changing over recent years. You get an idea of just what a dynamic planet we live in if you look at this. This is a simulation of the measured ocean currents that's happening. And just look at that, absolutely beautiful. The different currents are transferring heat around the world's oceans, and that leads to a whole set of larger scale movements, fundamental ocean currents that are moving not just water and heat, but salt around. You can see these interactions of the different oceans. And now we're moving, so in from the Indian Ocean, coming across. This is a thermohaline coming up into the Atlantic. And that one there is fundamental for driving, North Atlantic, fundamental for driving climate. And as a result, partly of that heating that's getting transferred, that heat transferred into the Arctic, is we're seeing the loss of the Arctic sea ice. So what we're seeing is just that diminishing year-on-year diminishment of the amount of sea ice, and also the ice extent in Greenland. So these are measured dramatic changes that are in our human timescale. It's extraordinary. And this is the net effect of that. This is what we call global warming. This is a global heating that's going on. We're tracking the global temperature changes for instrumental records, 1850s all the way through to the modern day. You can see the increasing effect of the temperature increase in the Arctic and the polar regions. But as we get to now, we see that more and more of the planet is above average in terms of its long-term temperature. What that takes us to is an uncomfortable reality for me as an earth scientist, because earth scientists on the one hand study the Earth's history and try and understand how it works. So that means that we understand its rhythms, its patterns, its sensitivity, its thresholds. So if you like, if you're worried about the planet, well, trust a geologist, an earth scientist to tell you about that. On the other hand, the reality of geology too is that we go out and find stuff. We go out and we find the energy, the fossil fuels, for example, that are causing that. We find the minerals that we dig. This is a super pit in Western Australia. The things that modern society wants to carry on in the way that we're used to. So we have this kind of split personality, really, of the geologist. The geologist is the earth exploiter, going out and finding the stuff that society needs for its phones, for its instruments, for its gadgets, for its technology. And then the earth steward, the earth scientist, is the protector, the guardian, the custodian of the planet as well. And it's kind of hard to reconcile those two sides, but they're really end members of a continuum. The earth scientist is in the middle, balancing out, counteracting these opposing kind of forces. And this is a good example. This is still probably the most beautiful place I think I've ever been. This is a Salar de Uyuni up in the Bolivian Altiplano in South America. Extraordinary place. Every year the rains wash materials down onto the flats of the valley, and it gets evaporated away to leave this salt crust that produces this perfect mirror. This is a UNESCO World Heritage Site, quite rightly. But it's also home to a third of the world's lithium reserves. Now, lithium is the lightest of the metals, and it's absolutely fundamental in electric vehicles, batteries for renewables. In fact, a lot of the technologies that we need for the low carbon future are connected to lithium. And so there is a danger that as we move into our low carbon world with these new technologies, these renewable green energies, that we're going to start to we will have to increase the resource base to supply that. And that may well mean trying to have to dig up places like this. And that is an ethical moral question that's really quite deep. So we end up in this situation where we are living in the most extraordinary point in Earth's history, that point there, when we've come out of 10,000 years of stable climate, a stable climate of the Holocene that allowed civilization to start, allowed farming to take root, the first cities to develop. So our whole complexity of modern society has emerged out of a nice, relatively stable climate. And yet it creates a force, humans, that essentially change that climate into a different climate and send us spiraling into a future that's referred to as the Anthropocene, the human planet, the human age, a time when humans are a geological driving force and changing the very nature of the conditions that they grew into. So it's an extraordinary moment, and one where we have to look to the future and say, well, where do we go next? How do we address, how do we confront these huge challenges that we've got in front of us, that we've made for ourselves? So for some people, the final frontier is up there. It's up there in space. It's back where we started. You know, it's terraforming Mars, or it's mining asteroids. But for me, you know, I kind of like it here. And my kids are going to be here, and I'm pretty sure my grandkids are going to be here. Most of humanity is stuck on this planet, and we need to sort this out. And I think one of the things that draws my attention is that maybe the future isn't up there in space. Maybe a big part of the final frontier is down here, the frontier that sits underneath our feet. As a geologist, understanding what's down there turns out to be absolutely critical. A few years ago, a geophysicist called David Stevenson came up with this idea that he published in Nature, talking about a mission to the Earth's core. It was bonkers, and it was tongue-in-cheek, but he said, look, what we need is kind of the equivalent of the space race, the moonshot, but we need it for the Earth. We need to go down and find what's down there. So he suggested, I think it was, you were going to go to the San Andreas Fault, create a megaton nuclear explosion to open up a crack, pour in liquid iron, and in that liquid iron there'd be a sensor, and that would go down, the density of the iron would take it all the way down to this core, and it would measure what's in the Earth. Completely mad. The point was, though, that technologically, if we put a mind to understanding the Earth the way that we've done with space, we could uncover the things that are just below our feet. And that was his main point. He says we live on the Earth's surface, which divides what is above from what is below. The part above us, the rest of the universe, is mostly empty, mostly unknown, and about 1,057 times larger by volume. The part below is crammed with interesting stuff, is also mostly unknown, despite its much greater proximity to us. So it seems to me that the expedition Earth really is not to go to the other planets, although the geology of the other planets is fascinating and geologists are involved in that. But it's that expedition to underneath our feet. And that is a spectacular place. This is the most spectacular place I've ever been. It's Nika Cave, Crystal Cave in northern Mexico. But these are very simple minerals. This is gypsum crystals, calcium sulfate. And yet they are spectacular. So it tells you that there are amazing worlds down there. And so this idea of exploring the empty outer reaches of outer space, I'd much rather be exploring these amazing places in inner space. And that's partly because of this notion becoming the green stone age, that in the decades to come, we will need to use just about every part of the periodic table to give us the elements to create these materials that we need for our new technologies, the technologies that are going to give us a low carbon future, get us out of fossil fuels, etc. And so whether it's wind turbines and solar panels at the moment, or graphene, or any of these things, we're going to have to be a lot smarter about using the Earth's natural geo-resources. The other thing about geo-resources that's underground is, of course, space. We were likely to be building our cities more and more downwards rather than upwards. That's partly through physical points. Cities can only get certain size laterally, they can only get certain size vertically, but actually there's a lot of space down there. And they're using that for storage and obviously transport systems, etc. But the city of the future may well have us living down there residentially. It's much more efficient for heat and for a lot of our kind of human kind of systems, logistical systems. But also, more importantly, perhaps in some parts of the world, they're going to be affected by by climate change, some parts of the world, it's going to be just intolerable to live and work on the Earth's surface. And so cities, for example, cities in the tropics and in many of the parts of Middle Eastern areas, it may well be that we need to start to develop cities underground. And therefore, the geological understanding of the properties of the resources down there is going to be absolutely critical. So for me, earth science, geoscience, is the study of the subsurface. That's the geologist's world. There's no one else that studies that world down there. It's a geologist's world, and we kind of understand it. We understand it enough to maximize our resources from it. This is a project that's going on just not very far from us in the Redruth in Cornwall. It's a deep geothermal project. That drilling rig has drilled the deepest hole in the UK, just over 5 kilometres down. It's intersected hot fluids coming off the hot granite from Cornwall, and it's going to drive geothermal energy, clean green energy from the inner earth. And it's exploiting technologies like this that our understanding of the subsurface is going to be critically important. So for me, the danger in all of this is doing it badly. If we exploit the earth in a bad way, the inner earth, then we're in trouble. And so I think we have to have a better understanding. The Terra Nullius needs some explanation. Terra Nullius is empty land. This was the kind of popular mandate that was given out to the colonial explorers who would say to places like Australia or North America, there's nothing there. Everything that's there is ours, because there's no one of any interest there. Well, I think it's a kind of sub-empty land. It's under a kind of empty subsurface. The notion that there's nothing really down there apart from resources that we can plunder. These are our hidden commons. The subsurface belongs to everyone on the planet, and so we need to have a management system to understand how we exploit that and do it in a sustainable way if we're going to deliver many of these fundamental UN Sustainable Development Goals, particularly those around about how we produce clean energy, economic growth, actually reducing inequalities. They're going to require resources, but we have to do it in a sustainable way. So usually with these things, I end up going back to Hutton. This is the Bolivia again, the quandary, the dilemma about whether we're going to be digging this stuff up for giving us our lithium. James Hutton, in the first paragraph of this theory of the earth, this outlandish big theory of how the planet worked, the first time we really had it, says, this globe of the earth is a habitable world, and on its fitness for its purpose, our sense of wisdom in its formation must depend. In other words, we understand the world in order to have sustainable human progress. It's about advancing and progressing humanity that our understanding of the earth is all about. And for me, that's a fundamental aspect about being a geologist in the 21st century. So we can do lots of things about projecting into the future with the plate motion. So this is the world, the future world that we think might exist in 250 million years into the future. But the critical thing for me is really what's going to happen in the next few decades and centuries. And so geoscience, earth science, geology, whatever we call it, for me is that. It's the science of sustainable human and planetary progress. And that should be the purpose and the ambition of Expedition Earth. Thank you very much.